NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we will build an intuitive understanding of the characteristic of a common logarithm. It is the integer part of log base 10, and it controls the size of the number. The remaining fractional part is called the mantissa. For any positive number n, we can write log of n equals c plus m, where c is the characteristic, an integer, and m is the mantissa, a number between 0 inclusive and 1 exclusive. Rule 1. If the characteristic is positive or 0, then the number of digits of n equals the characteristic plus 1. Example: the common logarithm of 200 is 2.30103. The characteristic c equals 2. Adding 1 gives 3, so n has 3 digits, which matches 200. Another example: if log of n equals 4.251, then the characteristic c equals 4. Add 1 to get 5. Therefore, n is a 5-digit number. Rule 2. If the characteristic is negative, its absolute value tells us the number of zeros to the left of the number, counting the single zero before the decimal point. Watch the pattern. Log of 0.1 equals -1. There is one left zero if you count the leading zero. Log of 0.01 equals -2. That counts 2 left zeros. Log of 0.001 equals -3. That counts 3 left zeros. Sometimes a negative characteristic is written with a bar. For example, log of n equals bar 3.251. The bar 3 means the characteristic is -3. Its absolute value is 3, so there are 3 left zeros, including the leading zero. That places n between 0.001 and 0.01. To make this visual, think of boxes for digits. A positive characteristic tells how many integer boxes you need. A negative characteristic tells how many zero boxes appear to the left, including the single box before the decimal. Summary: split log n into characteristic plus mantissa. If the characteristic is non-negative, digits equals characteristic plus 1. If the characteristic is negative, the absolute value gives the number of left zeros, counting the leading zero. These two quick checks let you estimate the size of n instantly from its common logarithm. Example: we will find how many digits are in the number a equals 2 to the power 50, given that log base 10 of 2 equals 0.3010. We will use the characteristic of a common logarithm. Start with the definition of a. Take the common logarithm, that is base 10, of both sides. Use the power rule for logarithms to bring the exponent down. Now substitute the given value. Log 10 of 2 equals 0.3010. Multiply by 50 to get 15.050 for log of a. A common logarithm splits into 2 parts: the characteristic, the integer part, and the mantissa, the decimal part. Here 15 is the characteristic, and 0.050 is the mantissa. The number of digits of a equals the characteristic plus 1. Apply the rule. The characteristic is 15, so the number of digits equals 15 plus 1, which is 16. Therefore, 2 to the power 50 is a 16-digit number. Recap. 1. Take the logarithm of both sides. 2. Use the power rule. 3. Substitute the given log value. 4. Read the characteristic and add 1 for digits. In this lesson, we will find how many digits are in the number 32 to the power 80, using the characteristic of a common logarithm. We are given that log base 10 of 2 equals 0.30103. We will follow the standard algorithm for the characteristic of a logarithm step by step. Start by writing a equals 32 to the 80. Since 32 equals 2 to the 5, a becomes 2 to the 400. Now take the common logarithm of both sides. Use the power rule. Log of 2 to the 400 equals 400 times log 2. Substitute the given value for log 2. Multiply to get log a equals 120.412. To count digits, we only need the characteristic, which is the integer part of the common logarithm. Let's split 120.412 into its characteristic and mantissa. The characteristic is 120. The mantissa, or fractional part, is 0.412. The number of digits of a positive integer, n equals floor of log base 10 of n plus 1. Using our value, the number of digits of a is floor of 120.412 plus 1, which is 121. Therefore, a is a 121-digit number. Example, we will use the characteristic of a logarithm to find how many digits are in a very large number. The problem says, if log base 10 of 3 equals 0.47712, how many digits does the number a equals 81 to the power 25 have? The key idea is, for any positive integer, n, the number of digits equals the floor of log base 10 of n plus 1. This floor part is called the characteristic of the logarithm. We start with a equals 81 to the 25. Take the common logarithm of both sides. Use the power rule of logarithms to bring the 25 down. Since 81 equals 3 to the 4th, we substitute and simplify. Then apply the power rule again. Now plug in the given value log base 10 of 3 equals 0.47712. Multiply by 100. That gives log a equals 47.712. The characteristic is the integer part of log, which is 47. Therefore, the number of digits equals 47 plus 1, which is 48. Let's show this clearly. In this lesson, we will prove an inequality using common logarithms and the characteristic idea. We are given the base 10 logarithms of 86 and 85. Our goal is to show that the quantity a equals the fraction 86 over 85 to the power 1000 is greater than 10 to the 5th. The clean way to compare a with a power of 10 is to take the base 10 logarithm. Start from the definition of a. Take the logarithm of both sides. Use the power rule. Log of x to the n equals n times log x. Use the quotient rule. Log of a over b equals log a minus log b. Substitute the given numerical values. Compute the difference inside the parentheses. Multiply by 1000 to get the final value of log a. The integer part of log a is called the characteristic. Here the characteristic is 5, and the fractional part, the mantissa, is 0.08. A characteristic of 5 means a lies between 10 to the 5th and 10 to the 6th. To build intuition, let's place a on a simple number line between 10 to the 5th and 10 to the 6th. We mark the interval and label the endpoints. Since log a is 5.08, a equals 10 to the power 5.08, which is just a bit to the right of 10 to the 5th. Therefore, the inequality is proven. A is strictly greater than 10 to the 5th, and because it is also less than 10 to the 6th, a is a 6-digit number. In this example, we will use the characteristic of a common logarithm to determine how many zeros appear after the decimal point before the first non-zero digit. We'll carefully follow the algebraic steps and then interpret the characteristic geometrically on a number line. Here is the problem. We are given two base 10 logarithms. Log of it equals bar 7.3010. Log of b equals 3.2020. We want to find how many zeros there are between the decimal point and the first non-zero digit of the product, a equals ab. First, take the logarithm of the product. Log of a equals log of ab. Using the product rule, log of a b equals log of a plus log of b. Now substitute the given numbers. Log is bar 7.3010. Log b is 3.2020. Recall the bar notation. Bar 7 means the characteristic is -7, but its mantissa remains positive 0.3010. So adding the characteristics and the mantissas separately gives -7 plus 3 for the characteristics, and 0.3010 plus 0.2020 for the mantissas. That equals -4 plus 0.5030, which we write as bar 4.5030. What does a characteristic of -4 mean? It tells us that a is between 10 to the -4 and 10 to the -3. Let's sketch a quick number line of powers of 10 and mark where a lives. Numbers between 10 to the -4 and 10 to the -3 begin as 0.000 something. In other words, there are 3 zeros immediately after the decimal point before the first non-zero digit. The rule is simple. If the characteristic is -n, then the number of zeros is n minus 1. Here n equals 4, so we have 3 zeros. Because the mantissa is 0.5030, 10 to that power is a number a bit larger than 3. So a behaves like about 3 times 10 to the minus 4, again consistent with 3 zeros after the decimal point. Final answer. The number a has 3 zeros between the decimal point and the first non-zero digit. In this example, we will use the characteristic of a common logarithm to count zeros after the decimal point. Here is the problem. If log base 10 of 2 equals 0.30103, how many zeros appear between the decimal point and the first non-zero digit in open parenthesis 1/2 close parenthesis to the 1000? Let capital A equal open parenthesis 1/2 close parenthesis to the 1000. Take the common logarithm of both sides. Use the power rule and the reciprocal rule for logarithms. Substitute the given value of log 2 and multiply. The characteristic is the integer part when the mantissa is chosen to be positive. Split negative 301.03 into an integer and a decimal part. Now adjust so that the mantissa is positive by adding and subtracting 1. That gives log a equals negative 302 plus 0.97. From this final form, the characteristic is negative 302 and the mantissa is 0.97. For numbers less than 1, if log a equals negative n plus m with 0 less than or equal to m less than 1, then a has n minus 1 zeros after the decimal point before the first non-zero digit. Here, n equals 302. Therefore, the number of zeros after the decimal is 302 minus 1, which is 301. Think of a as 10 to the power of negative 302 times 10 to the power of 0.97, so it is a very small number starting with 0 point, followed by 301 zeros, and then the first non-zero digit. Final answer. 301 zeros appear between the decimal point and the first non-zero digit in open parenthesis 1/2 close parenthesis to the 1000. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.